revisions in the going to start chapter 5, which is on trigonometric identities. And this whole chapter is going to be about how to solve equations using trigonometric identities, how to simplify expressions using trigonometric identities, and all that good stuff. All right, so starting with this one here. So the first thing we're going to talk about are identities that we actually already know, right? A trigonometric identity is basically two equivalent trigonometric facts that you literally set equal to each other, right? So take a look at this one. These are, right, all things that you know. So we know that sine is the reciprocal of cosine, right? Sine is 1 over cosine and vice versa. And cosine is the reciprocal of secant. So these we already know, tangent and cotangent. These are called reciprocal identities. And then we also know that tangent is sine over cosine, and the same for cotangent. These are called the quotient identities, okay? Nothing new here. So here, this is, that's completely up to you. So this is, you have cosine equals 3 over 4, right? You need to find secant of theta. Okay, this is like such a baby one. You will never be asked something this simple on a test. We're just kind of getting used to procedure, right? So we say secant of theta is equal to 1 over cosine of theta, which is equal to 4 over 3. And so, yeah, you can take a look at this just by looking. You're like, oh, it's 4/3. However, remember, it's never about the final answer. It's about the process, right? And so when you're asked to justify, that is the justification, okay? So secant of x, look at this one. Secant of x is 5 over 4. Tangent of x is this. We need to find sine x. So this is what we have, and this is what we want. What you want to do in this case is you want to relate the thing that you want to what you have in a trigonometric identity, right? So I know that tangent of x is sine x over cosine x, right? And I have sine x here, but I have secant here, right? Well, I know that cosine x is 1 over secant x, so cosine x is 4 over 5. All right, coming back here, I need to find sine x, right? So I multiply this by cosine, I multiply this by cosine, so I get that sine x is cosine x tangent x. And now what's cosine? 4/5. Tangent, 3/4. So this is 3/5, and that's sine x. Again, you're never going to have something this simple, right? But it's the process more than everything else that counts, okay? All right, yeah.
So when I did this, I plugged in the values for tangent x and secant x. Is it fine if I solve like that? Or?
Okay, like I said, you're never going to have something this simple, but everything we solve here is going to be done using the identities, okay? Another question you might have is, I could just draw a triangle and do this. Yes, you can, but in this chapter, we're doing identities. So you are not going to be allowed to solve using triangles in this chapter. You can check your work using triangles, but you have to show all your work using identities, okay? All right, very quickly, and then I need to move on.
So we always have to say like cosine x.
Yeah. Again, let's do a couple like actual ones that you're going to have. All right, let's move on to some of the other identities. We know that if we have a right triangle, right, and like this one over here, and if this is x, and if this is y, I know that x squared plus y squared is equal to 1 squared, right? That's the Pythagorean identity. Or in other words, I know that y squared plus x squared is equal to 1 squared, right? Now, in this case, if I have a triangle like this inside a unit circle, I know that this y is actually sine of theta, right? And I know that this x is actually cosine of theta. So another way of writing y squared plus x squared equals 1 is sine theta squared plus cosine theta squared equals 1. Now, this is one way of writing it, but a more concise form of writing it is sine squared theta plus cosine squared theta, and that equals to 1. And because this comes from the Pythagorean theorem, we call this a Pythagorean identity. All right? Now, this is like knowing 1 plus 1 equals 2, right? You just need to know. There is no way you can be in a pre-calc class and not know sine squared plus cosine squared equals 1. You need to commit this to memory. Now, this Pythagorean identity has friends, right? If I take sine squared theta plus cosine squared theta equals 1, and just for fun, if I divide everything by cosine squared theta, okay, let's see what I get. What's sine over cosine? Tangent. Sine squared over cosine squared is tangent squared theta. Plus cosine squared over cosine squared is 1 equals, what's 1 over cosine? Secant, but if it's squared, it's secant squared theta. And you can see that this is another one of the Pythagorean identities. All right? Now, correct. No, something, because like 5 divided by 5 is 1, not nothing. Okay, let's do it again, and then I'll take another question. This time, let's divide by sine squared theta, because it's fun and we can. Oh, equals 1. Right? So now, sine squared divided by sine squared is 1, plus cosine over sine is cotangent. But when they're squared, it's cotangent squared theta equals 1 over sine is cosecant, so this is cosecant squared theta. And oh my God, that's the other one. So we have 3 Pythagorean identities. You will not be provided these on a test or a quiz. You need to know them. However, it is necessary to absolutely know the first one, and then you can always derive the other ones. Or by the time like we use everything, you'll hopefully just learn them. Okay? All right. Yep.
For like any of them, could you just like square root the whole thing?
No, let's use them, and we cannot do that. You cannot take a square root of like.
But then wouldn't it cancel out?
No. You can't, if you have x squared plus y squared and you take a square root, this is not equal to x plus y. That is not correct mathematically. Okay? Yeah.
Couldn't you move one of the terms to the other side and then
Okay.
take the square root of that one side?
Okay, so why don't we actually use them so you see, because we can ask what if any, but okay, I think some people are having trouble believing me about this. If you have 16 plus 25 in a square root, that's the square root of 41, correct? Okay, is that the same as 4 plus 5, the square roots? No, that would be 9. Like it's like wrong. Okay? It's wrong. Okay. All right. So let's do a couple of these. Okay, so if cotangent is 2 and cosine of theta is less than 0, find sine and cosine. This is identical to the problems that we did in chapter 4, which we solved with triangles. Here, you're not allowed to use triangles to solve them. So let's first figure out the quadrant. Here it says cosine is negative. That means it's in these 2 quadrants. Cotangent is positive. That's in these 2 quadrants. So my angle is in quadrant 3. Okay, now I have cotangent. I need sine and cosine. Okay, you always want to start with an identity that has what you have. So here, one of the identities that has what I have is this one. So let's start with this. Cotangent squared theta plus 1 equals cosecant squared theta. All right? Now, cotangent squared, cotangent is 2. 2 squared plus 1 is cosecant squared theta. So this is 5 equals cosecant squared theta. Take a square root, take a square root. Cosecant theta is plus or minus root 5. However, you could only have one answer. In quadrant 3, cosecant is negative. So it'll be cosecant of theta is negative root 5. Okay, that's great, but it's not what I'm looking for. What I'm looking for is sine. Sine of theta is negative 1 over root 5. So that's one thing that I need. Another thing that I need is cosine. Okay, I have cotangent, I have sine, I need cosine. I know that cotangent of theta is cosine of theta over sine of theta. Okay? So now if I multiply both sides by sine, I get sine of theta, cotangent of theta, is equal to cosine of theta. Sine of theta, negative 1 over root 5. Cotangent is 2. So cosine theta is negative 2 over root 5. Okay? Yes.
How did you determine that it was quadrant 3?
We did this. Remember?
Yeah, but how did you?
Because you're told cosine is negative. Cosine is negative in these two quadrants. You're also told cotangent is a positive value. Cotangent is positive in these two quadrants. The one quadrant where two symbols match is this one. Like in each of the other quadrants, you only have one option, right? This is where both of them are true.
What if you have two positives and two negatives?
You will never get a quadrant with more than two symbols in there.
Right. So what if you get?
It doesn't matter. It doesn't matter if it's two positives or if it's two
Would it
negatives.
be that quadrant?
It will be that quadrant.
So just the one that has
Just the one that has two. This is the same thing that we were doing in the last chapter, remember, that some people were not doing and you're not getting the negatives correct. Yep.
For like the first equation when we write like cosine squared of theta,
Uh-huh.
we did that because the x squared plus y squared is n squared, but then how did we get cosecant squared of theta? Like where did that?
That's this identity. This identity that
Oh,
we
we're
use.
just using that equation.
Right. Okay? Okay. So let's talk about cofunctions. Okay? Cofunctions are this. So do you want tissues? So have you wondered, okay, why it's sine and cosine, secant and cosecant, tangent and cotangent, right? Like what is the relationship between them? So the relationship between them is the following, right? So suppose this is 30. Oh my, rearranging furniture. Suppose this is 30 and this is 60. Okay? And so then this is 1, root 3, and 2. Okay, now, what's sine of 30? A half. What's cosine of 60? 1/2. Right? For any right triangle, when two angles are complementary, their cofunctions are the same. So 30 and 60 make 90, correct? That means sine and cosine of those two will be equal. Tangent and cotangent of those two will be equal. Okay? So if I have, let's put it another way. If I have sine of 40, right? The cofunction of sine is cosine. It'll be the same as the cosine of the complement to this, which is how much? 50. And so if I have secant of 20, what will that be equal to? Cosecant of 70, right? Because together they add up to 90. Another way to write it is if I have, let's say, sine of theta, this will be equal to cosine of pi over 2 minus theta, or 90 minus theta. Okay? So these are the cofunction identities. Okay? So you can take a look. Cosine, like sine is cosine pi over 2 minus 90. Notice the order. It's not theta minus 90. It's pi over 2 minus, because you can't have a negative in there. Let me do a couple and then I'll take questions, okay?
Actually, never mind.
Now, next, let's talk about odd and even identities. We've actually talked about this a little bit because we had some homework problems on it in the last chapter. Sine of negative theta is negative sine theta. Do you remember doing this? Where we had, theta, and we said this is the sine of it. And then if we have negative theta, now this is the sine of it. And if this was, let's say, positive 3, this will be negative 3. So when you go between theta and its opposite, the sign will also become opposite. Cosine, however, will stay the same. So cosine of negative theta is the same as cosine of theta. Tangent will also be opposite because it's dependent on the sign. Okay, so now, here we have sine of x is equal to 4/5. This is straight out of last chapter. What would sine of negative x be? Negative 4/5. Okay, now, what about this one? Cosine of pi over 2 minus x. Cosine of pi over 2 minus x, we know from the cofunction identities, is sine of theta. Okay, so this is just sine of theta, or sine of x rather, which is just 4/5. Okay, let's do another one. Now we're given cosine, okay, equals this. We need sine of pi over 2 minus x. First, you see this and you're like, oh wait, that's just a cofunction identity. So sine of pi over 2 minus x is just cosine x, correct? Which is how much? Negative 0.75. Okay, but how is this different? It's not, it's the negative, right? It's opposite, it's the negative. So this is the same as sine of negative pi over 2 minus x. Right? Nope. Okay, so if you have 3 minus 5, that's the negative of 5 minus 3. Is that right? Right, parentheses. So now, what is this then? What happens to this negative if you have sine of negative something? The negative will come out, right? So this is negative sine of pi over 2 minus x. This is negative cosine x, so it's positive 0.75. Okay? So when you go home tonight, think about that. Okay? Like, reason it out. Reason it out. So simplify and rewriting trigonometric expressions. So you're going to be told to simplify trig expressions. And of course, like, it's always like, okay, how simplified is simplified, right? Well, basically you want to put it in a state where it's no longer possible to do any further operations to it. All right. So there are many ways to go about each one of these. I have here one type of the different types you might have on your homework. Okay. So let's start with some tips. All right. One good tip is start by rewriting it in terms of one trig function, right? So either all sines or all tangents or all cosines. Another one is rewrite things in terms of sine and cosine only, okay? So let's take a look at this one. To do these, you have to use the identities that we've gone over, right? Now, in each lesson, we're going to add to these identities. So you're going to have more to choose from. Right now, we have, all of these. So, you have 1 over cosine here, which we can't do much about. Cosine is preferable to secant. But take a look at what you have here. This is a telling sign. What you have here is 1 and then added to or subtracted from a trig function squared, right? So if you have sine or cosine squared or tangent squared plus or minus a 1, you have to immediately think Pythagorean identity. Now, the Pythagorean identity that has sine squared is this one. Okay? Now, these identities are not rigid things. They could be maneuvered and, the order can be changed as it suits my needs. So here, what I have is 1 minus sine squared. I want to make this look like that. The way in which I can do that is subtract sine squared x, sine squared x. So here I have cosine squared x is 1 minus sine squared x. Oh my God. 1 minus sine squared x is exactly what we have here. So I can substitute that. So let's see what I have. 1 over cosine x, I'm just rewriting, times. What's 1 minus sine squared x equal to? Cosine squared x. And so now cosine squared over cosine x, right? It reduces to cosine x, and that's the most simplified version of this. Okay? All right, let's do another one. Here, this is another type. Look at this. I got cosine tangent sine cosine squared. Okay? I have a plus here or a minus, and then, so I have 2 terms. Okay? Okay, there's more than one way to do this. I'm going to just choose one of the ways to do it. And that is the following. I have cosine, sine, cosine. This one kind of stands out. It's a tangent. So why don't I start with writing this as sine x over cosine x minus sine x cosine squared x. Now, these reduce, right? So I have sine x minus sine x cosine squared x. Okay, how many terms does that have? 2 terms. What's common in both of them? Sine x. So what if I factor out a sine x? When I do that, what do I have from this first term? 1 minus cosine squared x. Okay? That's it. What is 1 minus cosine squared x, though? Sine squared x is right. So this is sine x times sine squared x for a total of sine cubed x. You see that? Okay? So, yep, yes.
The instruction said in terms of sine and cosine only.
Yeah.
Does that mean the part of like sine x minus sine x times cosine squared x? Isn't that in terms of sine and cosine only?
Yeah, but there is also operations that could be done. Not only that should it be in sine and cosine, but also no operations should be possible. Okay, this one, I have two fractions, which I'm adding and subtracting. Common denominator. Okay, so let's do a common denominator. What's the common denominator going to be here? What? Well, 1 minus secant x, 1 plus secant x. Okay, so to make this a common denominator, I need to multiply this by 1 plus secant x, 1 plus secant x, and then this one, 1 minus secant x, right? Okay, so what do I get here? I get secant x, 1 plus secant x, minus secant x, 1 minus secant x. Take a minute and just write down some work, right? Okay, so this is equal to now when I distribute secant x plus secant squared x minus secant x plus secant squared x. All over, what happens if I multiply this? 1 minus secant squared x. Fabulous. Okay? It's a plus b, a minus b, so it's a squared minus b squared. Okay, now, oh look, secant x minus secant x goes away. What's secant squared plus secant squared? 2 secant squared x. Okay, here I have 1 plus or minus a trig function squared. Which one of my Pythagorean identities has a secant squared? Oh, the second one. Tangent squared plus 1, I'm going to do this on my scratch paper. Tangent squared theta plus 1 equals secant squared theta. So what's 1 minus secant squared theta? Negative tangent squared. Right? Because there is a little bit of like cross there. So this is negative tangent squared theta. Okay, let's simplify this a little bit more. So what's secant squared? 2 so it's 2 cosine squared x. No. Sorry. It's 2 times 1 over cosine squared x, right? So it's 2 over cosine squared x. Right? Secant squared, this is 2 times 1 over cosine squared x. So it's 2 over. Okay. This one, negative sine squared x over cosine squared x. Cancel, cancel. Negative 2 over sine squared x. And this is good enough for me because it's in terms of sine and cosines. In the book, it might also be written as negative 2 cosecant squared x. That also works. The point is there are no further operations. Okay, let's do this one.
Wait, which one do you want us to use?
Either one of these is okay. Okay, 1 plus, okay, so here we go. 1 plus tangent squared x. What's that equal to these days? Secant squared x over cosecant squared x. Okay, so what do you suggest we do now? That 1 over cosine squared x, right? This is 1 over cosine squared x, 1 over sine squared x. So this is the same as 1 over cosine squared x times the reciprocal, right? So that is sine squared x over cosine squared x, which is tangent squared x. And again, either of these are okay. Okay, last one. Remember LNs? Yeah. Okay, so properties of LNs. ln of a times b is ln of a plus ln of b. ln of a over b is ln of a minus ln of b. And then ln of a to the n is what? What happens to the exponent? No, my God, it goes away. It goes and becomes a coefficient, right? So it's n ln of a. Okay? Now, we can also go this way, right? If I was walking down the street and on a billboard, I just saw ln of a plus ln of b, I would say, oh my God, that's ln of a times b, right? Of course it is. So if I have this, right, I can also rewrite it. Now, what's the domain of ln? Can you have ln of a negative number? No. Can you have ln of 0? Also no. But you can have ln of a positive number. So look at ln of sine x. Is it ever possible for sine of x to be negative? I mean, yes, right? Because sine of x, half of its life, sine of x is positive, and half of its life, sine of x is negative. So if you want to have ln of sine x, you want to make sure the sine x is always positive. That's why it's necessary to have absolute value sine x. Okay? So if you have ln of a minus ln of b, this is the same as ln of a over b in absolute value. This is ln of tangent x. Is it ever possible for tangent to become negative? Yes. I mean, right? So then you must have an absolute value. Now, what if you have ln of, I don't know, cosine squared x? Okay, the square does go to the front. But before we do that, does this, the way it stands, need absolute values? No, because cosine squared is positive. However, it's not simplified, so you technically can't leave it that way. The simplified form of this is if this goes down, 2 ln of cosine x, but you have to have absolute values here. Okay, before I take questions on this, listen. Remember how in honors math we need to be sophisticated, elegant math students? Look at my steps here. Look at how in between each step I have equal signs, right? Without the equal signs, this is not math. This is just a series of random symbols that are meaningless. If you want to make this real math, you have to have equal signs where they belong. Okay? All right, question.
If you had like the number e, sine, cosine were an absolute value, you explain a solution.
Oh, if it was given to you like that? Yeah, it wouldn't though, because it wouldn't make sense.
Okay.
Yeah. Yeah.
You said that like ln of cosine squared x